Nwacc, Survey of the Universe, Lecture 21, Galaxies, Part 2, for Wednesday, April 15th, 2020. Please take notes on this video. There is an example at the end. Please do the example with me. Today's classwork, which is posted to Canvas, is based on the example. It's due Thursday night, April 16th. So let's begin now, as we usually do with poetry. Say it with me. When distance matters, use the distance ladder. In the solar system, bounce a radar. Parallax for a nearby star. Nearby galaxies aren't terrible, thanks to Cepheid variables. For galaxies far away, type 1a supernovae rule the day. And if a galaxy has no candle at all, use Hubble's law. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. So now let's talk about the evolution of galaxies. Why it is that galaxies look so different. Why is it that we can put galaxies into these two buckets, spiral and elliptical, and then there's this third bucket here where all the weirdos go, the irregulars. What you're looking at here is a timeline. 0 here is the Big Bang, the beginning of the universe. Over here is present day, almost 14 billion years after the Big Bang. When we look at the Hubble Ultra Deep Field, at some of the first galaxies that were in the process of forming, they all look irregular because they haven't formed their structure yet. By about 4 billion years after the Big Bang, we start to see disk galaxies, and shortly thereafter, those disks form spirals. We also see ellipticals very early on, and the average size of those ellipticals grows with time because ellipticals are hungry, they're cannibals, they like to swallow other galaxies. Remember that to look far away is to look back in time because it takes light time to get here. Light travels very quickly. By human standards, it travels very quickly across this room, 186,000 miles per second. That's very fast on Earth, but it's very slow in space. It just creeps along. It's taken 14 billion years almost for light from the first galaxies to reach our telescopes. So the farther away you look, the farther back in time you look, which is why when you look at an image like Hubble Ultra Deep Field, you are actually seeing the evolution of the universe in real time. You can see galaxies that are brand new, which means you're looking at the present day. You can see galaxies that are a billion light years away, which means you're seeing the universe a billion years in the past. You can see galaxies that are 10 billion light years away, which means you're seeing the universe 10 billion years in the past. So to look at a deep field like the Hubble Ultra Deep Field, this one right here, you are actually seeing the universe evolve in real time. We also have computer simulations that try their best to simulate the evolution of the universe. Now let's be clear, any computer simulation we do of the entire universe is greatly oversimplified. We don't even have the computing power to model a single galaxy in its full complexity, right? To say nothing for the entire universe. Nevertheless, if we're willing to accept an oversimplification of our model, the models of the universe look pretty good. Oversimplified, but pretty good. This simulation is called the Millennium Run. It starts out with a cubic universe, one shaped like a cube. Okay, we know the universe is not shaped like a cube. That was just mathematical convenience. You put a whole bunch of particles here that are shaped more or less like what we think the universe would have been shaped like very early on. And then you let gravity do its work. And the Millennium Run, this particular simulation, is famous because the end result is, in fact, the structure that we see in our telescopes. That's what you want with computer models. You want the computer models to end up with something artificial galaxies that look like what we actually see in our telescopes. So with the combination, the interplay between theory and data, between computer models and telescope observations, we've developed a story, a theory of how galaxies formed. The universe is full of gas, mostly hydrogen, good bit of helium, traces of other things. The denser regions of that gas contracted first to form what we now call superclusters of galaxies, which then further contracted to form galaxy clusters, which then further contracted to form galaxies. Those early galaxies had lots and lots of globular clusters. These, remember, are huge star clusters with hundreds of thousands, sometimes even millions of stars all born about the same time, which means the most massive among those stars are going to blow up supernova very quickly, like setting fire to a fireworks stand. Pow, 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 supernova all over the place. And those supernova, the collective shock waves from the supernova, will push the gas away from the globular clusters. Well, it takes gas to form new stars, so when the gas is pushed away from the globular clusters can no longer form new stars. But in most cases, over half the cases, the gas is not completely pushed away from the galaxy, which means it can collapse to form a disk. If so, that galaxy will become a spiral. However, if there are so many globular clusters that all the gas is pushed out, there's nothing left to form a disk, and you get an elliptical. So then that begins to explain why we have these two very distinct types of galaxies. Spiral galaxies that are shaped like disks, and elliptical galaxies that are shaped like eggs. If a protogalaxy, a galaxy that's being formed, is very dense, then you have a whole lot of supernova happening all at the same time, and they push all the gas right out the galaxy. So you get an elliptical. Stars don't collapse to form disks. Gas does. However, if the galaxy is less dense, if it's more diffuse, then yeah, the supernova will push the gas away from the globular clusters, but not all the way out of the galaxy. There will still be gas left in the galaxy to collapse into a disk. And that disk will form spiral arms and will continue forming stars right up to the present day. So the density of the protogalaxy will have a huge say in determining what the galaxy will end up looking like. If the galaxy was denser, it's more likely to be an elliptical. If it's less dense, more diffuse, it will more likely be a spiral. How fast the protogalactic cloud is spinning also matters. If it's spinning faster, then it'll have more angular momentum, which means it will be more likely to collapse into a disk. But there's another way for elliptical galaxies to form. When spiral galaxies collide, they merge to form an elliptical. And the reason for this is when the two spiral galaxies collide, their gas compresses. Each galaxy compresses the other galaxy's gas, producing a huge burst of star formation. We call that a starburst. Starburst galaxies have so many stars forming at the same time that the most massive among them are going to blow up, go supernova, all at the same time. Again, think of setting fire to a fireworks stand. Pow, 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 pow. The collective shock wave from all those supernova will push the gas right out the galaxies. So what's left over when two spiral galaxies merge is an elliptical, because there's no gas left to form a disk. According to both simulations and telescope data, galaxies were closer together earlier in time, which makes sense, right? The universe is expanding, so if you turn back the clock, the galaxies get closer together, which means they merge more often earlier in the universe. And because of this, most of the early galaxies that we see are still in the formation process, and they're irregular. They're being harassed by the gravity of other galaxies, which means they can't settle down to form nice, beautiful, symmetric disks with fragile, symmetric spiral structure. Remember, spiral structure is fragile. If another galaxy gets too close to a spiral galaxy, the disk will warp and the spiral structure will be erased. And that's what we see in the earliest galaxies. When galaxies get too close to each other, they compress one another's gas, producing a starburst, a burst of star formation. We see this in telescopes and also in computer models. And we like it when computer models actually match what we see in telescopes. They don't always. Sometimes you make a simulation and it does not work and you just have to start over. So here's telescope data, 2 galaxies in the process of colliding. Each galaxy is ripping the other galaxy's stars and gas off and throwing them out into space. We call those tidal tails. There's one here and one here. And if you have a good simulation, you can reproduce this effect. 2 spiral galaxies merge. The first thing they're going to do is warp. Each is going to warp the other's disk. There's going to be a huge burst of star formation, which is not shown here. Then each galaxy is going to fling the other galaxy's stars off into intergalactic space. Those are tidal tails. The whole time they're dancing around one another because they're co-orbiting their common center of mass. And then eventually they're going to settle down into an elliptical because their gas will have been flung out and pushed out by the supernova from all of those new stars. So when you have a whole lot of galaxies in really close proximity, they're going to merge a lot, and that means they're going to be ellipticals. Galaxy clusters are regions with lots of galaxies in close proximity, and they're nearly always filled with elliptical galaxies. Spiral structure is too fragile to withstand the tightly packed environment in a galaxy cluster. Our Milky Way is not in a cluster, it's in a group that is a much smaller, looser association of galaxies. So our spiral structure hasn't yet been warped or wiped away by the gravity of another galaxy. But give it time. In 3 billion years, the Andromeda Galaxy is going to merge with the Milky Way, and they are going to collide, and they're going to merge and form an elliptical galaxy, which we call Milkomeda. Galaxy clusters eat galaxies. If a galaxy gets too close to a galaxy cluster, the galaxy cluster's gravity will suck it right in. And if it gets too close to the center of the cluster, then the giant elliptical at the center will suck it in and eat it. Elliptical galaxies are hungry. They're cannibals. This is a real word. Galaxy cannibalism, when one galaxy eats another. So we study galaxy evolution by an interplay between telescope data and computer models. When computer models match what we see in our telescopes, we say, okay, that's a pretty good computer model, but all computer models are oversimplified, so that doesn't mean you're done. If your computer model matches what we see with telescopes, that means your next job is to try to make your computer model be less oversimplified, more detailed. Increase the detail as much as your computing power will allow, and then check again to see if it matches what we see in our telescopes. On the other hand, if your computer model doesn't match what we see in our telescope, well, then you got to go scratch your head and start over. So the reason we have spiral galaxies and ellipticals is that if a galaxy, a protogalactic cloud, that is a galaxy in the process of forming, was diffuse, then the gas was able to settle into a disk and form spiral structure. If it was really dense, however, then there would be too many supernovae early on, and the collective shock wave from the supernovae would push the gas right out the galaxy as soon as it's formed, so there's no gas left to collapse into a disk. Now, the centers of galaxies are not all the same. Some galactic centers are much, 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 much brighter than others. We call particularly bright galactic centers active galactic nuclei, or AGN. We say that they are active. It was the discovery of active galactic nuclei, particularly quasars, which are the brightest active galactic nuclei, that gave us the first clue that there may be black holes at the centers of galaxies. What we're looking at here is an active galactic nucleus. It's very bright, and there is a jet of matter, of charged particles moving outward at nearly the speed of light. And the reason for that is what's powering this active galactic nucleus is a supermassive black hole, just like Sagittarius A star, though much, much more massive. Sagittarius A star, the black hole at the center of the Milky Way, remember, is 4 million times the mass of our sun. This one, the one in the center of M87, is more like 6 billion times the mass of our sun. So it's over 10 times the mass of Sagittarius A star. It's if an AGN is particularly bright, we call it a quasar. The word quasar is a really cool word. I just like walking around saying the word quasar for no reason. It is a portmanteau, which is a contraction without an apostrophe. It means quasi star. Or quasi star. The reason it's called a quasi-star or quasar is when the first quasar was discovered, it looked in the image like a star. You thought it was a star. So when you discover something new in astronomy, the first thing you do is look at its spectrum, look for its spectral lines, figure out what it's made of, how far away it is, how hot it is, and so on. But they couldn't find the spectral lines. They looked at this thing and they're like, where the hell are the spectral lines? We can't find any at all. Well, they took more and more observations, so they call it a quasi-star. It looks like a star in the image, but we can't find the hydrogen lines. Well, they took got better and better data, and they eventually did find the hydrogen lines, but those hydrogen lines are way redshifted. Here are hydrogen lines in the laboratory, and here are the same lines in the first quasar, which is named 3C273. They're so far redshifted that told astronomers that it has to be really far away by Hubble's law. But that was baffling. If this quasi-star is really that far away, we shouldn't be able to see it at all in the tiny little telescope they were using. If they could see it, and it was really that far away, it would have to be ridiculously bright, like 1 trillion times the luminosity of the sun. That can't be right, can it? I mean, there's the evidence. So astronomers first thing they did, as scientists always do, is look for how they could be wrong. Is there anything else that this could possibly be besides an object 1 trillion times the luminosity of the sun? Because we've never seen anything like that before. They ruled everything else out. So then they had to start asking themselves, what in our Rolodex of objects in physics could possibly power such a thing? And they scratched their heads. Nothing that's been discovered could possibly be 1 trillion times the luminosity of the sun. But they started thinking, didn't Einstein say something in general relativity about what do you call it, a black hole? An object in space with so much gravity, if you cross the event horizon, nothing can escape, not even light. Well, yeah, but they're not real, right? But if they were, could they produce enough gravitational potential energy to power something 1 trillion times the luminosity of the sun? Compute. Well, yeah, you could. In fact, the black hole is the only thing known to physics that could do that. So that was the first clue. Now we have much more compelling evidence. The first clue that quasars might be powered by black holes. Here's a thought question. What can you conclude from the fact that quasars have very large redshifts? Is it A, they're generally very distant, B, they're more common early in time, C, they might be turned on by galaxy collisions, or D, nearby galaxies might hold dead quasars? Well, that is a trick question, sorry, because the answer is yes. Large redshifts means very distant, that's Hubble's law. To look far away is to look back in time, so if quasars are very distant, that means they were more common early in time. The universe is expanding, so if you turn the clock back to the early universe, galaxies were closer together and they were colliding more often, so C is correct as well. And if galaxies early in the universe were more likely to be quasars, and galaxies nowadays are not, that suggests that quasars have shut off, that nearby galaxies might have been quasars in the past. Maybe even the Milky Way had a quasar in the past. And indeed, when we often see quasars that are in the process of merging with other galaxies. I should say, we often see quasars in galaxies that are in the process of merging with other galaxies. What this tells us is that both galaxies have supermassive black holes at the center, but once the galaxies collide, each galaxy starts feeding gas to the other galaxy's black hole. And when that gas spirals into the black hole, it heats up. It heats up to millions of degrees. So hot, it glows like an Edison light bulb. A really bright Edison light bulb. 10 trillion times the luminosity of our sun. Bright enough to be seen billions of light years away. Here's the spectrum of a quasar. On the y-axis, we have brightness, how bright the quasar is, at various wavelengths on the x-axis. The visible rainbow is right here. There's infrared to the right of that, radio to the right of that. To the left of the visible rainbow, you have ultraviolet and then X-ray. Things to notice, there are 2 peaks. That means the quasars are not all the same temperature. You have the inner part, which is hotter, because it glows mostly in the ultraviolet. You have an outer part that is cooler, which glows mostly in the infrared. And a few quasars also throw a lot of radio waves at us, though not all. Quasars that do throw a lot of radio waves at us, we call them radio loud. That simply means that they are loud in the radio spectrum. Here is the nucleus here's an active galactic nucleus right here. And what's happening is the black hole has a really intense magnetic field that draws plasma, that is charged gas, out the north and the south pole and shoots them out like jets. And while those particles are traveling at near light speed, they just cut through the interstellar medium. But eventually they collide with gas and slow down, so they spread out. This is what happens if you smoke or vape. Just say no. But if you do, when you blow out the smoke or the vape, the smoke is a nice cone when it comes out of your mouth because it's moving fast. But once it interacts with the air, then it poofs out. Likewise, this black hole is smoking, spewing its gas out at nearly light speed, so it makes a nice cone that could in fact be bigger than the galaxy itself, 100,000 light years or more. But eventually it's gonna slow down enough, because it's been colliding with gas the whole time, that it's going to spread out, just like smoke filling a room. So these jets, as they're called, these jets are sometimes larger than galaxies themselves. They go all straight out the galaxy that they're in. And when particles spiral around magnetic field lines. They often emit radio waves. And so that's why these galaxies tend to be radio loud, the galaxies with big jets. Usually in astronomy, we only get snapshots of things, right? We can't look at the evolution of a galaxy. It takes too long, right? You can't look at a galaxy and see it evolve. You can take pictures of 100,000 galaxies, each in different stages of evolution, and then get real data on how galaxies evolve. We do that. We do that with stars too, right? We see young stars, we see middle-aged stars, we see old stars, we line them up on a timeline and compare that to what we know about physics, and that's how we know how stars evolve. We cannot look at a single star evolving. But there are a few exceptions. There are a few things that we can see actively happening. Stars exploding, supernova, we can see that. And jets coming off of radio loud quasars. So these are jets. This is data showing jets, radio jets, that are emanating from an active galactic nucleus. Here is the jet in 1991. In 1993, it's expanded. 94, expanded further. 97, it has expanded farther still. I made a mistake in my terminology. Radio loud AGN are not quasars necessarily. What you're looking at here is called the bagel model. An active galactic nucleus has an extremely bright center, 1 trillion times the luminosity of the sun, but it's surrounded by a bagel-shaped cloud of dust and gas. If we happen to be looking right down into the bagel, we're going to see the quasar. We're going to see the trillion solar luminosity center of the galaxy. On the other hand, if we're looking at the bagel from the side, then we're not going to see it. It's going to be brighter than normal, but we're not going to see the quasar. What we'll see are the jets. So this is more likely to be a radio loud AGN if we're looking at the bagel from the side. If we're looking right into the bagel, it's more likely to appear to us as a quasar. So an active galactic nucleus can be extremely luminous, 1 trillion times the luminosity of the sun. Luminosity also varies rapidly. It gets really bright and really dim very quickly. That tells us that the thing is small. It's compacted down to something the size of the solar system. Because if a thing were really large, like the size of a whole galaxy, for example, since our galaxy is 100,000 light years across, it would take 100,000 years for an increase in luminosity to travel from one side to the other. So a large object brightens and dims slowly. But a small object, like a quasar, can brighten and dim very quickly because it doesn't take long for an increase in luminosity to travel from one side to the other. I should say from the center to the edge. There are multiple peaks in AGN spectra, which means they have more than one temperature. They're hottest in the center. And some of them drive plasma jets out the north and south magnetic poles of the black hole at nearly light speed. And when you put all of this evidence together, the only thing in our understanding of physics that could do all of this is a black hole. An object in space with so much gravity, it pulls space and time with it as it spins. And once you go into a black hole, nothing escapes, not even light. And you might ask, well, why are they bright then? The black hole itself isn't bright. The gas that is spiraling into it is bright because it is spinning at nearly light speed, producing lots of friction. And what does friction do? Heats things up. And in the case of gas falling into a black hole, it heats up to millions of degrees and glows with the light of 1 trillion suns. The jets are from the twisted magnetic field lines of the black hole. Here's the black hole. Here are the twisted magnetic field lines. Those magnetic field lines capture charged particles and move them outward at nearly light speed. The charged particles spiral around the magnetic field lines. Here's the accretion disk right here. Black holes are a big part of the galaxy evolution, we think. There are reasons to suggest that a black hole grows with the galaxy, though that is not certain. One way that we measure the mass of a supermassive black hole at the center of a galaxy is by looking at the accretion disk. Remember, you determine an object's mass by watching other things orbit it. With Sagittarius A star, we can watch stars orbit it. With nearby galaxies like Andromeda, we can watch stars orbit it. With quasars, they're usually too far away. We can't see individual stars. What we can see is the gas that's going around it. So we can tell how fast the gas is moving by taking a spectrum of one side and then the other. Well, the side that's moving away from us is going to be red-shifted, and the side moving toward us is going to be blue-shifted. And the difference between those two peaks is going to give us the orbital speed, and from that, we can estimate the mass of the black hole, though there's a big margin of error in that. So every galaxy that we've been able to take a measurement and answer definitively yes or no, the answer has been yes, there's a black hole at the center. That doesn't mean there's a black hole at the center of every single galaxy. Remember, there's 100 billion galaxies within range of our telescopes. So every one, all, is a big number. There could be exceptions, I'm saying. But all the galaxies where we've actually been able to take a measurement, the answer's been yes. And it appears that black holes become active galactic nuclei when they're eating a lot of gas. When there's a whole bunch of gas in the vicinity, that gas spirals down like water swirling down a drain, spirals down at nearly the speed of light, producing a lot of friction, causing the gas to heat up and glow with the light of 1 trillion suns. So it may be that most or all galaxies or galaxy centers were quasars at some point in the past. It may be that our Milky Way galaxy had a quasar in the center, that Sagittarius A star, the black hole at the center of the Milky Way, was at one time a quasar. But we don't know. This is the active galactic nucleus at the center of the galaxy M87. Its mass was estimated at about 4 billion solar masses by the orbital speed of the gas. However, that has been updated to 6 billion times the mass of the sun by this image right here. Oh my God, forgive my cussing, holy shit. This is an image of a black hole that was taken in 2017 and released in 2018. The dark place right here is what they call the shadow of the black hole. It's about twice the size of the event horizon. You're not seeing the event horizon itself. You're seeing a radius about twice the size of a black hole. And then this is the accretion disk. The gas is orbiting this way in this image. And the reason we know that is that the bottom is brighter than the top. There is an effect in relativity called relativistic beaming. Things coming toward you at near light speed will look brighter. Things moving away from you at near light speed will look dimmer. So the gas down here is brighter, it's moving toward you. Gas up here is dimmer, it's moving away from you. Well, if that's the case, why can we see it all the way around? The accretion disk looks something like this. Well, remember, a black hole, it has a lot of gravity, and gravity is a lens. It bends light. You can see behind the black hole. That's general relativity for you. There is a correlation that's well known. The more massive the bulge of a galaxy, the more massive the black hole is going to be. This suggests, though doesn't prove, that the black hole grows with the bulge. It might be that the bulge has some gas in it, and the more massive the bulge is, the more gas it has to feed the black hole. And so the more massive the bulge, the more massive the black hole is going to be because it's eaten more gas. So that suggests that a black hole develops and grows alongside the galaxy. However, there are alternate hypotheses to that. The idea that a black hole grows with the galaxy runs up against some issues in the data. And that is that when we look back to the very earliest galaxies, the galaxies in the very first stages of formation, some of them already have fully formed AGN, 1 billion or 10 billion times the mass of the sun. So if galaxies grow slowly along with their, if black holes grow slowly along with their galaxies, you'd have to explain why it is that some are already fully formed. So there is an alternate hypothesis that black holes formed first, shortly after the Big Bang, through gravitational waves smashing into each other is one possibility, though there are several hypotheses here. And then galaxies grew up around the black holes. Not only does the mass of a black hole correlate to the mass of the bulge, it also correlates to the tightness of the spiral arms. The more massive the black hole, the more tightly wound the spiral arms. This correlation was discovered by the Arkansas Galaxy Evolution Survey at the University of Arkansas and UALR. And it's a little bit misleading. You might think, oh, okay, well, that makes sense. If the black hole is more massive, then its gravity is pulling on the spiral arms. Not the case. No. The black hole is a monster in its own regime, but the spiral arms are too far away from the black hole to be affected significantly by the black hole's gravity. The reason we think more massive black holes are in galaxies with tighter wound spirals is the bulge. The bulge is feeding the black hole. The more massive the bulge, the more massive the black hole. Also, the gravity of the bulge is pulling on the spiral arms. The more massive the bulge, the more tightly wound the spirals. So the correlation between black hole mass on the y-axis and how tightly wound the spiral arms are on the x-axis is due to the bulge. This x-axis is the pitch angle. That's how tightly wound the spiral arms are. A low pitch angle means more tightly wound spirals. So up here we have very tightly wound spirals with really big black holes. Down here we have very loosely wound spirals with very small, relatively small black holes. But again, it's not cause and effect. The black hole's gravity does not reach far enough to pull on the spiral arms. The black hole, we think, is being fed gas by the bulge, and the bulge is also pulling on the spiral arms. So, it appears that all or nearly all galaxies have supermassive black holes at the center. And we're not sure how they formed. They may have formed with the galaxy itself. They may have formed before the galaxy. Some of those black holes are in the process of eating gas. And as that gas spirals inward, it spirals into the black hole. It travels at nearly the speed of light, producing a lot of friction as it bumps into other gas particles, which heats it up to millions of degrees and makes it glow with the light of 1 trillion suns. We call those quasars. The mass of a black hole is correlated to the size of the bulge, the mass of the bulge, and also the tightness of the winding of the spiral arms. And we think that's probably because the bulge is both feeding the black hole gas and pulling gravitationally on the spiral arms. Oh, you've made it through galaxies. All right, well, let's do some poetry. Say it with me. Sitting callously at the center of a galaxy, a black hole can swallow whole a star or become a quasar by heating the gas it's eating. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. Here's a summary slide, which you can use to help you study, and another one, and another one. Let's do an example of Hubble's law. And this is also on a classwork that is posted. Hubble's constant is approximately 22 kilometers per second per mega light year. Isn't that a strange unit? It's really an inverse time. It's a frequency. Using the linear approximation to Hubble's law, estimate the distance to a galaxy with a recessional velocity of 88,000 kilometers per second. B, convert your answer to light years. Well, let's do that. We start by just writing down Hubble's law. V equals H naught D. Now, this is algebra. We always ask ourselves the same 4 questions. What am I solving for? What's cluttering it up? How is it attached? And how do I get rid of it? So what am I solving for? It says estimate the distance. So we're solving for D. All right, what's cluttering it up? H naught. How is it attached? It's multiplied. How do you get rid of something that's multiplied? You divide. So we are going to divide both sides by Hubble's constant, H naught. And on the right side, H naught cancels. That's the whole reason we did that. And I'm going to swap across the equal sign. Distance then is the velocity over H naught. That's cool. Let's put in our figures here, but we're going to have to do something with these units. So the velocity is 88,000 handwriting lessons, no kilometers per second, divided by 22. Here's this weird unit again, kilometers per second per mega light year. Remember that capital M is mega. Mega means million, per million light years. The numbers are simple. You put them in your calculator. You'll get 4,000. Okay, put them in your calculator. What we really need to deal with here are the units. Let's do that. You have kilometers per second here divided by this fraction, kilometers per second per mega light year. To divide by a fraction, this is the key to everything here. To divide by a fraction is to multiply by its reciprocal. So kilometers per second divided by kilometers per second per mega light year equals kilometers per second times mega light year per kilometers per second. Now that also looks weird, except we have a kilometers per second on top and one on bottom. Boom, they cancel, and we're left with mega light year. So the unit is mega light year, or million light years. So now we can give an answer. D is 88,000 divided by 22 is 4,000 mega light year. All right, did you do it with me? Do it with me. Don't just watch me do it. You don't learn by watching, you learn by doing. If you didn't do it with me, pause the video and do it. You got to do it yourself. It's the only way to learn. Now let's do part B. We're going to start with the answer. 4,000 mega light years. Well, mega just means million. Mega light year is a million light years. So we'll substitute. That is 4,000. And remember that units are always multiplied. So a mega light year is a million light years. So that's 4,000 times 1 million. You can put 1 million or 10 to the 6th. If you remember 10 to the 6th is a million. Either way will work. Light years. Be sure and put unit, light years. If you just put numbers, it's meaningless. Now, you can put that in your calculator and come out with a number. Or you can recognize that 10 to the 6th is one with 6 zeros after it. So 4 times 1 is 4. You have 3 zeros here, 6 zeros here for a total of 9 zeros. So that's 4 times 10 to the 9th light years. Equivalently, maybe you put it in your calculator and it gave you a decimal, so that's just 4 billion. But if you're gonna draw a bunch of zeros, be sure and count the zeros in your calculator. It is easy to miscount the zeros. Put one too many or one too few. So 4 times 10 to the 9th light years, acceptable answer. 4 billion light years written out, acceptable answer. You could even write it out in English. 4 billion light years, also an acceptable answer. Questions on that? Like you can, sorry. I'm used to saying questions like that. All right. Oh, don't make me do every single one. Come on. There we go. I'm learning technology. Here's a solution that doesn't look like my handwriting.